Bello quello. Eh sì, sono lunghetti e ti serve qualcuno. Mancano
Hello.
Fabrizio e Fauno, ma arrivano quando arrivano. Il cellulare. Aspetta, scrivo un attimo.
Se manca qualcuno?
Sì, però gli scrivo.
Quarto d'ora.
Scrivi il font che hai usato.
Computer mod. Andate. Hello. Ok. Hi. Hello, hi everyone, and this applause was also for you that came with, showering rains and terrible days. So thanks to you for coming to this exciting new format for Papers We Love. It's our first lightning talk session. Even our speakers gave up, at least one. Fortunately, they had a problem at home, so they couldn't come. So it's only the two of us tonight, and hopefully it will be good enough. But that's a good pro for lightning talks, because if it were just one speaker, then we wouldn't have no talks. So, so that's a good reason for making more lightning talks. So you're welcome to do them. It's Jack's first talk, apparently.
Yep.
That's what he said. And this will be probably my worst performance because I didn't prepare enough. But that's another story. So you can be better. That's the point. All right. Okay, what's Papers We Love? For people that don't know, Papers We Love, it's a community, global community of people that like to talk about papers, reading papers, and also discussing papers they don't like, which is what I'll do tonight. And the idea is to create a network of people that like computer science, work in innovative computer-related places, connecting academics in Milan, And so, all right, these are our links, github.com. This is where often you can, where you can share your proposals, but there's also a call for paper link for later, the other page. There's a Twitter that I still call Twitter. No, it's Twitter. The Eventbrite to get the tickets, and the Discord. Nobody's really on the Discord, but there is a Discord. So if you'd like to have a chat with us, with the speakers that attended the talks, that delivered the talks tonight, we'll be there. And again, this is the call for paper link. If you want to propose a paper, full length or shorter length, please do. We actually have already a speaker in the pipeline, which is a first, or at least it's a first in the last few months. So it's going to be, again, about LLMs. I don't remember the topic exactly. Model collapse. All right. So I think it's going to be in June, but we haven't scheduled a date yet. Probably end of June, right? Right. Okay, cool. So let's start. Let's give it up for Jack.
There's a ratio of speakers to public that is quite high. Okay, I'll move to the other one, which hopefully is going to be here. Oh, the top and bottom are going to be ugly. That was unexpected, but we'll take it. So hello, everyone. I'm today presenting a paper that touches the concept of cellular automata and tries to extend the most famous game of life into a continuous space. It's a very simple paper, and it's going to be a relatively quick and simple presentation. So just quickly, a few words about me. I am Giacomo. I used to be a software developer with a passion for game design. Now the situation has switched, but it is basically the same. I keep studying. I keep coding, and I am definitely not an expert on anything I'm talking about today. That is the point. The point of it is that it is Papers We Love is just about some cool paper we find and we want to talk about. Doesn't have to be about our life's work, even though it could be, and it could be also pretty good as well. Anyways, talking about cellular automatas. Oh, sorry, no, before that, just a few links. The presentation is on GitHub. The paper is, of course, on Archive as always. The presentation has been done with Motion Canvas, which is a pretty fancy TypeScript-based tool to generate presentations via code. It's quite, it has a lot of boilerplate, unfortunately, and the code is going to be really ugly if you check it out. But it is actually quite powerful, and I'm trying to harness it as I can today. So we're talking about cellular automatas. Oh, ciao, Fauno. So, just in time. So, anyone else? No. OK. we're talking about cellular automata. So broadly speaking, a cellular automata is a mathematical model of some kind. It is meant to work with cells, where cells are individual elements connected between them in a graph. They can be alive, they can be dead. Usually they are in a sort of a grid, and they usually are in a sort of a grid, and at every step of the state of the system, each of them can be alive or can be dead. Every iteration after the first, every step that follows, the state of each cell can change based on criteria, usually something around the surrounding cells, the way they're connected, and that's about it. That's the broad definition of a cellular automata. It is generally considered a computational model because it's meant to be simulated by something. It is also an abstract model that doesn't represent anything in reality. It's not a simulation of reality. It's just some model that exists and that follows its own rules. And because it's made on points in a graph, it is discrete. It's quite simple. The cool thing of all of this, though, is that even though it is a very simple thing with very simple rules that anyone can learn, the kind of emergent behavior that you get out of this can be quite surprising. There are a lot of things that happen, and that's why people study it. So approaching the concept of cellular automata from the simplest thing ever, which could be a one-dimensional cellular automata. Well, a zero-dimensional one could be simpler but kind of dull. One-dimensional cellular automata means that you have a line of cells in a row, and each of them interacts with the one nearby. An example we can see now is the one from Stephen Wolfram, which is considered one of the simplest ones, of course. And the rules of that is that for each cell, the cell checks the neighbors and the state of the cell itself. And based on these four different rules, which is basically if there is one cell within the neighborhood or if there is two cells on the right, notice it's asymmetric, the cell is considered alive, otherwise the cell is considered dead. Very simple. What you get is you start from one alive cell. If it's all dead, of course, nothing happens. And it multiplies, then it gets asymmetric, then it gets more asymmetric, and it goes on and on and on. It's not particularly interesting on its own, but if you look at it, putting each line on top of each other, basically every step of the iteration, you get that you already start to see some kind of patterns out of it. It's nothing mind-blowing, but it's there. Moving from the simplest kind of cellular automata to the most famous, which is, of course, Game of Life, I am expecting, I think most of you already know it, but I need to talk about it anyway, so I promise I'll be quick. It's a two-dimensional cellular automata in this case. It's conceived by John Conway, and it is a 2D grid. It doesn't have a rule for each configuration. It would be quite annoying to memorize. It simply counts the cells that are surrounding each cell we're analyzing, and it checks just a couple of rules based on how many neighbors are alive at a certain iteration. So if there are 2 neighbors alive and the cell is already alive, the cell remains alive. If there are 3 neighbors, the cell becomes alive no matter what. Otherwise, the cell is dead no matter what. It is just that. You have the rules for aliveness, rule for death, and that's it. So applying this to a grid, in this case it's a 2D grid, what you get is that if you have a single cell in the center, the cell will just die because there is no neighbors. If you have already 2, yeah, dies as well. But if you get to 3, you get that at this point you are already getting a pattern that is repeating somehow, because at the iteration after, you get that the 2 on the right and left get alived and the top of bottom get unalived. So you get something that is similar to before, and it gets back to before, oscillating over time. A more interesting pattern is actually this one, which I put on the bottom left for a reason, which is something that has a repetition pattern, like a period of 4 iterations. On the second iteration, it actually becomes ugly, but then on the third iteration, well, yeah, on the third step, it becomes identical to itself, but shifted, and then again ugly, and then it gets the initial one shifted. So you get something that is moving. Sure, it is an object, but it is an object that appears a lot, and it is an object that gets created just out of nothing, and it's kind of cool. And this is the glider. The glider is the simplest form of particle that you get in Game of Life. There are many others, of course. A lot of them, these are just a few. It doesn't matter, though, because what's interesting here is that you get already some families of different kind of patterns recreating. The glider and the spaceship are moving diagonally and horizontally. You get things that oscillate. The blinker oscillates with a period of 2. The pulsar, I don't remember, with a period of a lot. Not even that much, but yeah, a bunch. And then you get like stable objects like ice, a tub, and a beehive. And then the puffer, which is just messy, likes to make mess. It's kind of fun. Point is, there is a lot of stuff that can happen in Game of Life. It doesn't matter that much for us, but it's worth checking for what we see after this. Let's just get like a random situation, because I'm using motion canvas. Let's use it for some logic there. And let's let it run. You can see that there are patterns emerging here. It's very simple, nothing crazy, but you get a couple of eyes, the diagonal eye, which is weird. Sometimes we get oscillators. Every time is different. So, oh, there is a glider up there. That's actually cool. And, well, whatever. It's Game of Life. Anyways, from Game of Life, let's move to the continuous space. That's the interesting concept. It's actually quite simple, but it has a few interesting steps. So the concept of what you get with a cellular automata is that it has a few constraints defined by the universe. So it is discrete mostly. It is discrete in time and space. It has discrete states. It has discrete interaction, as in like dynamics. You count the amount of elements around. That's it. It's that you don't do weird math. And the interaction is local. You just go with the neighbors. So we can destroy each of these dogmas without destroying the concept of a cellular automata. So starting with the simple cell of Game of Life, one cell and the neighborhood, the easiest thing to do is just to like extend the neighborhood. Why don't we just have an arbitrary range R? That's easy. The local interaction is gone. And at that point, it makes sense to be like, OK, but different ranges might have different values. And that's definitely not discrete because trigonometry. So we get some donut, and the discrete dynamics are lost. OK, so we are summing together. We are adding together values that are not discrete. Probably the state of the cell can also be non-discrete. Doesn't need to be just alive or dead. It can be something in between. And that's gone as well. And the last step, which is just go to the infinite. So OK, we have a step which we basically reduced in space and in time. We can do it more. So we just zoom back, we expand, and again, we get the same thing. And we can do it again and again, and basically we get to the infinity. So we lose the discrete space, the discrete time, because we have infinitesimal steps for both. It is still a game of, not a Game of Life, a cellular automata, but it is fundamentally different. It is something deeply different, but also we saw that for each step, we didn't change the base concept behind what it is, so it's also quite the same. It is abstract, it is deterministic, it creates emergent behaviors, it's fine. So on this concept, there are a couple of papers. I say one, but it's actually two. So the two papers that appeared over the last 2 decades, whatever, are Smooth Life and Lenia. Smooth Life is a simpler approach that simply tries to extend what we have, making it into something continuous, simple as that. There has been a few others of these. It's a whole family of the greater than life sort of paper family. And Lenia is one that got into a weird obsession over creating different kind of universe with different parameters. It's a bit more technical, so I decided to just focus on Smooth Life. It's the right thing for this topic, for this format, sorry. So the Smooth Life paper has a very humble presentation. It just tries to generalize Conway's Game of Life. It is a simple concept on its own. We already described it before. They actually do a couple of fancy tricks to make it work well, because what we want more than anything is emergent behavior of some kind, like cool things happening. And to do that, they try to emulate what the cell and the surrounding used to be, because if you just get a point in space and try to get the state out of that point, it gets very wobbly, like the chaos rapidly gets into full noise of everything. So what they do is create two values, which are integrals of specifically a surrounding of each point that we're analyzing and a ring around that point. And each of those gets an integral of the state of the cell there into some clearly non-discrete value. In a clearly non-discrete value. And that's already something that makes it a lot more sturdy. But it is a continuous space. We get hard boundaries there. That's not nice. So they implement also step functions, which make it blurred. And that's also a step forward into something that is more stable, less prone to boundary conditions. This is basically what the paper does. It does nothing else. It proposes an implementation of this, but the trick key part here is that there is quite a few parameters at this point because you have all the step functions, the parameters, the ranges, like the radiuses. Like you get quite a few different parameters. So they propose a few sets of solutions like that. But that's about it. That's all they do. It's a 4-page paper. It's quite readable indeed. The implementations, however, can be quite various. So the point is, for each point in space, we want to have a sum, an integral of something that is around that point of space. This is a convolution. There's nothing more than a convolution. We are in a discrete space because even though we're in the continuous space, we have a computer, so it is discrete. So we're working on a discrete convolution. And that's exactly what Game of Life does, only much bigger because at this point we don't have just 8 neighbors. We have a pretty big amount, which is like it depends on how fine we want to simulate, not on the rules of the game itself. So in that sense, the easiest way to do a convolution, of course, is brute forcing it. You have, for each cell, which is already a lot of cells, you want to check on the surrounding cells, which are potentially a lot as well, and check the distance between the two. Depending on the distance, you put them under some weight function into one or the other bucket, which are the states of the inner part and the outer part that we saw before, the orange and the yellow one. This goes with basically n to the 4th. In terms of efficiency, that's not really good. A much easier solution, but it's not easier, it's just faster, is using FFTs. FFTs are sort of magic, so when you move stuff into the frequency domain and multiply it point by point, you get a convolution, so that's very convenient. You just need to know what an FFT is, how to use it. There are very fast implementations of it, so I'm sure lots of people did it, but there is a simpler way which it is actually easier to understand, and at the end of the day, it's comparably fast, if not faster, for a small simulation, which is using GPUs. So using shaders, the code of shaders, it's kind of the same of the brute force. It's literally just brute forcing stuff. But this time, we're running on a lot of this different processing units, and that makes it OK. There are sort of a trade-off where, depending on the radius or the amount of points, this GPU is just like basically like being, OK, use the FFT, please, but that's not a problem for representation and in general to play around with this thing, which is really nice. So let's look a little bit more about the shaders, mostly because they're really cool and because, I mean, why not? So they are simply snippets of code that you can just send to the GPU, compile and send to the GPU instead of running locally. And they have a bit of a limitation because they have to be sent there. You have to prepare to package every information you want to send them. But if the simulation is just a state, which is just a buffer of memory, it is relatively usable. They're highly parallel and not really fast on their own, but really fast as a group. And they can be used for a lot of stuff, not just graphic, not just video games. Speaking of video games, the simplest way to see a shader is something that gets some input, which can be geometry, which is the usual way you do rendering for all that kind of stuff, and puts out some pixels on screen. Each pixel is calculated independently, and you get your screen image. If you want to do a simulation, you can do the same. You just put in some noise or some initial state of any kind, and you get your first iteration of the simulation. You want to have more, so all you need to do, which is kind of painful to do in code anyways, is to save it as a buffer. So you get the output, you put it as the input, you repeat, you have your simulation. It is general purpose. You can use it for a lot of stuff. Generally, shaders work on a 2-dimensional space, which is not great, but there are ways to avoid that, of course, obviously. But that's how I used it, because it makes sense on a 2D map like the one of Smooth Life. So the implementation that I'm going to run now is taken from a Shadow Toy implementation that someone did. I don't remember the name. It was a bit of a... Anyways, he's really cool. And he has other implementations too. This one in particular is super short. It is 200 lines of code, but it's probably 50. The rest is mostly like handling some commands, some fancier initial noise generation, not really important. And it's this. In this case, it's running in motion canvas, so it is a bit less efficient. But you get things happening. And if it doesn't work, I can go back and run it again. It's different. So we get things. They're moving too fast. You get gliders that are moving, and moving even wobbling a bit, because each of them is starting from a state which is not perfect, even though there is a bit of an attractor towards that. you get stable objects like these dots, which is quite a few of them. There are bigger ones too, and you get bridges, like those two dots are connected by something that looks like noise, but is extremely stable. And other stuff, it's kind of empty this time, but hey, that's what we got. Anyways, there are quite a few of other patterns that we can see and that I put into my conclusions. So I spent quite a bit of time hunting for patterns of fancier times, and there are some nice ones. So there are two kinds of stable patterns, which is not obvious because it's not just an upscaling. It's not like stable patterns of all size. There are small ones, big ones, and that's it. And I don't know why. There are gliders, but then there are double gliders that they go together for quite a bit. All of them are relatively short-lived because noise, because my implementation is actually kind of crappy compared to the one on Shader Toy, and because in general it is a continuous space, and there are even rotating ones. I only found one. I stopped everything and screenshotted it immediately because it's really cool. They just rotate around each other, and it died after a few seconds, unfortunately. And then you get the bridges, which again I find fascinating because they don't have a circular symmetry of any kind, even though the kernel is circular, and they're just there, and they work. So we get all this stuff. It has a bit of a similarity to what we got with Game of Life, even though it is not Game of Life, clearly. But it is a universe. It follows its own rule within its constraints. It creates patterns. It creates things. You change the parameters. You get a different universe. Each of them on its own is a universe of some kind. I find it fascinating. I find that there is some parallels with particle physics in the sense that if you look very, very closely, maybe you get something like that in our case. Who knows? It's really nice. Well, a lot of people know, not me. It depends on the parameters. So again, you can have a lot of different kind of things, just like in Game of Life. Game of Life, usually you stick with the parameters because it's cool enough, but you can actually get different kind of games of life, and you can get very different kinds of n-dimensional cellular automata in the continuous space as well. And the species and patterns that created, you get multiple of them with the same parameter, which is kind of astonishing for me. And I think it's really cool. And the fact that it looks really cool, it's probably the most important because it's a paper we love, and I loved it for this reason. Just a couple of suggestions of books because I think they're really cool. They are novels. They are not textbooks, but they can be a bit cranky sometimes. Both of them touch the concept of cellular automata from different directions. And I mean, it's great gig, and sometimes you have to skim over the pages, but it's really nice. Both of them are really good books. And I think that's it. I think this is the end. So it's gonna, yes, start again.
How COVID was born.
Yes, basically. You just run a lot of those, you get COVID for sure. If you have questions, I'm going to look at it because I want to see fancy stuff. But I'm also going to listen to your questions. I'm just going to have an eye to Bennett.
Questions?
That thing is like,
Yeah.
and it's a double glider with a. Okay, that's really
It was.
Well, it's recorded, so
Yeah, everything.
right. Oh, it's the simulation. That's nice. Okay, I can watch it
Next.
later.
What's next in your path to this? If
look
anything?
more of that.
I'm actually done. I just saw a very cool paper. I just wanted to talk about it. I played a bit with shaders. I was happy. But from my point of view, it was just a really pretty thing that was the perfect topic for the first Lightning talk.
What was the hardest part to bring it into motion canvas? The shaders or the Game of Life?
Definitely shaders. The main point is that like using shaders on its own, like when you look at shader code, it's beautiful. It's short, it's simple, it's mathematics. And it's not even difficult mathematics. It's literally just a sum in a loop. The problem is that it needs to be initialized properly, otherwise the GPUs get throw a tantrum, yes. And when you need to have a buffer, again, it is something really simple if you're doing on WebGL or whatever on web, but if you're using something else, it gets a bit tricky. It's initially meant just to deform what you see on screen on another thing. If you want to have a loop, there are very simple ways to do it. This is clearly not one. And the funny thing is that since the simulation is supposed to be based on individual pixels, you're working on a buffer, but the shaders, the way they're done, because again, they're not compute shaders, they're not meant for actual simulations. In hindsight, probably I should have just used a compute shader. But these ones actually work on a space that is defined in a value between 0 and 1 on both directions. So when you pick the value, it might interpolate it. There are ways not to do it. But I actually found that the way I was doing it, it's good enough, but I actually found that there were a few weird things happening because it was actually approximating two ways, like when picking and when storing, and it was actually creating a bit of noise because of that, which is like not optimal. Yeah, but it's fun to play because at the end of the day, when you write the code itself of the shader, it's super easy. That one is it's absolutely simple to read.
There was
Ma prendo quello ambientale.
Did you experiment with other parameters to see the changing on the simulation?
In fact, I did, because even if I really didn't want to. I really wanted to have something looking nice for the presentation. I played before on my own, but not a lot. The problem is that I wanted it to be full screen, and the parameter that I had, the set of parameters that I had, worked on a certain size. Again, since everything is not pixel-based, but it's based on the actual dimensions, but then there is an approximation due to the fact that the pixels I'm using are not that small. Like a single object is maybe 20 pixels around. So it is actually a pretty strong discretization of something that is supposed to be continuous. The initial parameters I was using, that is the same that are used in the shader toy one, which I might open later. It's actually a bit prettier, but quite similar. They didn't work as well. So I had to play around quite a bit to find the right ones. The kind of species that you get are very similar. But in Lenia, which is the other paper, they focused on something that they call basically, like they created a taxonomy of species. And they created hundreds or thousands of different species. They had a lot of, it's PhD people, they had a lot of time to just click and simulate and look at pretty stuff. But the problem is that each of these species existed with a certain set of parameters. There are no species in Lenia coexisting with the same set of parameters because, I mean, they were focusing on creating different species rather than creating a diverse universe. This is cool because it goes on, it doesn't die. Most of Lenia's implementations eventually die, and they just become all black, or they all get swamped by basically a white noise, not even like basically the pipes, but everywhere, and then you just get that. This is a good set of parameters, and even here, when I was trying, I was playing with different sets, and some of them, most of them ended up being barren, and most of them, the other half of most of them ended up being completely swamped in just something that looks a bit like the initial noise of the first stage. It doesn't get out of that. But yeah, like even playing with those parameters, I got slightly different size of gliders, or because like if you increase everything, basically you get the same object bigger. So yeah, and it goes on. Oh, the big one, the big static one there. Nice.
Thank you.
was another question. You? No? Good? No? All right. Thank you.
I mean, no, I'm good. Vero? Poi c'è la GPU che va al 100% fissa.
Infatti si sta chiudendo il tavolo.
Questo decolla, fa proprio... è un drone. Scusa.
Ah, se no usavo il gelato.
Vabbè, tanto.
Stacco?
Visto che vuoi lamentarti del video, non puoi gesticolare per me.
Ah, giusto.
Fermo qua.
Sì.
Così sei con mani libere.
Grazie.
Qua. Te?
Grazie.
Guarda che service.
Mamma mia, guarda, veramente.
Qua siamo anche wireless. Cioè,
Ho sbagliato carriera.
sì, davvero.
Vabbè,
Ci vedo
è ancora in
delle
tempo.
cose che siamo registrati.
Esatto. Allora. Here we go. What? What's that? All right. Okay, so these are my notes. I won't need them, but all right. Yeah. Yep.
Facciamo tipo un appello dicendo
Mhm.
se lo fate
Se vuoi farlo intanto. Ah, ok, sì. Sì, prendi tempo.
prendo tempo mentre fa.
Se vuoi registrarla con il microfono.
No, non c'è problema. Due parole solo su Papers for Love. Should I do it in English?
Stai trasmettendo ancora?
Sì, sì, sto.
Okay, I'm gonna go in English. So just a few things about the lightning talks. It is something that we started and that we proposed basically. So at the end of the day, this time it was me and him, and it was the two of us plus that proposed it to begin with. And so there hasn't been a lot of participation so far, but I really think it is a great format. Like 15 minutes means that it doesn't have to be a really complicated thing. I talked about something that you can have during like a eating a pizza. You can talk about it. That's the level of the conversation, but still, it is actually something that it's easy to transmit with a bit of love. So I would really recommend to everyone here to think of some topic. It can be a paper, it can be a blog post, because at the end of the day, we're talking about it's basically the same thing. Something cool that you found somewhere and you want to talk about for 10-15 minutes, and it will become 20 minutes by the end of your preparation anyways. And if I did it, I just had absolutely no confidence in that specific topic. I think everyone can do it, so please come forward, because we need people.
All right. All right, so that's the next topic. So I like to talk about compilers, but you know, LLMs are all the rage, so here's the paper about LLMs and compilers, and that would have worked better if we had the first talk about LLMs, but all right. So the specific reason I wanted to read this, I actually wanted to read this paper. So that the whole reason why I started, I did the lightning talk, well, there were two. We didn't find a third speaker, and that's true. And I actually wanted to read this paper because it's connected to something I'm doing daily for a job, and I'm going to show a demo. The agenda is not really important. We're going to go through basically the paper's outline. And by the way, this presentation has been almost fully generated by an LLM because I didn't bother to do it myself. And that's just to tell you how sloppy I was this time. Anyway, that was surprisingly good. So I almost didn't change it. So that's a good point for LLMs. All right. So I don't know if you're familiar and you used LLMs in the past. So ChatGPT, Claude, So they're pretty cool, but nowadays they've been, empowered to call external tools like web search. They can do thinking, whatever that means. They can call external services. Now this paper is from the last version is June 2024, which means about 20 years ago now. So it's kind of outdated, and there's been a lot of improvement in the last few months actually. And there's also a follow-up about doing parallel function calling in a different way. Anyway, this was kind of a first, I think, and so it was interesting. So the whole point, what's function calling, and why are we interested in a parallel compiler for LLMs function calling? So essentially, the point is LLMs just generate text, and we want to be able also to interact, give them, they're kind of brains without arms and legs. They cannot interact with the real world. So how do we make them interact with the real world? We give them the possibility to interact with the real world. How? So we give them the power to do function calling. I don't know if you can read that there, but I'm going to read it for you. Function calling is the capability to invoke external tools to overcome inherent limitations expanding beyond content generation. So the idea is this is just a machine that is able to generate text, but we want it to also invoke a service. So we give it this name, function calling. Sometimes is tool use, same thing. Current methods, however, I'm going to introduce function calling, but the point of the paper, this is the abstract of the paper. Current methods have drawbacks. Basically, these LLMs generally generate text sequentially. And so the tool invocation that they're able to do, are inherently limited by being able to generate function calls sequentially. So that means that you can only invoke functions sequentially. So what could we do to improve the situation? How could we make it possible to invoke functions in parallel? Right, that's the point. Right, but the point is, the question is, don't most LLMs just generate text? How does this work, really? So it's text generation all the way down. Looking to extend my LLM with function calling. Ask support if function calling is just JSON text gen. Support doesn't understand. I pull out an illustrated diagram explaining the difference. Support laughs and says, it's a good function calling, sir. I try function calling, it's JSON. So, I don't know if you recognize the meme, but it's okay if you don't. The point is, the way they work is they generate more text. How do you make something to generate text invoke a function? You just generate more text. That's how you do it. So what's function calling really? It's a piece of middleware. So function calling is generating text. The text is generated in such a way that you can interpret it somehow. You put in the middle between you and the text generator something that captures the output, intercepts the outputs, interprets the outputs, and does the real function calling, in this case, for you. So when a function call is found, the middleware intercepts it, actually invokes the function, pastes back basically the results into the text stream, token stream. You feed back the token stream into the text generation machine. The text generation machine generates more text, and you go on and on, back and forth. That's how it works. So yeah, the function call really is a serialized request to invoke a given function with some given parameters. When I was explaining this to someone that wasn't fully aware of how these things work, and actually was working on some completely different area, actually compilers and WebAssembly, which is my area currently, I was explaining to them how this would work, and I was saying, oh, that's kind of interesting. It's like, if you think about it, it's kind of like the I/O monad works in Haskell. And I was like, that's a great way to put something that is so banal. I mean, yeah, in a way. So well, how does the I/O monad work? So really what a Haskell program does is concatenating the description of a program that does effects, that is, interacts with the external world, that does something that it's effectful. And the Haskell program itself is pure. It's just, it is not doing something that is effectful, but the runtime that runs the Haskell machine is capable of doing the effects. So this is kind of like an escape hatch that makes it possible for Haskell to claim to be pure while actually be something that interacts with the word, so that it can actually do something useful instead of just heating up the room. So it's a great way to put it, but I would rather say that it's more like remote procedure call. It's not that, I mean, yeah, in a way, it's kind of like Haskell works. But you know, in computer science, there are a lot of similarities, different things, and you can find a lot of fancy way to describe the same concepts after all. So yeah, that's kind of a remote procedure call. Right. I'm working for a company, it's a very small company, startup, American, yeah, the Ellipso, called Ellipso, and we work with WebAssembly, and we have an open source framework to plug WebAssembly into your code, and you can write plugins using WebAssembly, and you can plug these runtimes. Then we run plugins for written WebAssembly in any language, so both the plugins can be written in any language, and the runtimes can be plugged in any language, so you have both sides. And recently, because this was so hard to explain to a customer, well, in a way, but yeah, this is, what can you do with this? Pretty much anything. So what's a use case? Anything where you can plug code, and really there's a lot of use cases where this is actually already happening in the wild, like Shopify has a way for you to customize the shopping cart with custom code, and they use WebAssembly. There's a lot of example of WebAssembly in the wild. This is another example, something that we built. It's called MCP.run. I don't know if you're familiar with MCP, and it's a way essentially to plug these functions in a standardized way. It's called the Model Context Protocol, and I'm going to go through whatever that means. But essentially, as I said, you provide a way to the LLM to describe a function call, and you usually use JSON schema. And then the model has been post-trained to know how to generate text that represents a function call, that is another JSON payload. The idea with MCP is essentially, so usually what the middleware, the piece of middleware that I described earlier could be part of your code, like just a function, or it could be an external service. And MCP essentially, the Model Concept Protocol, is a protocol that standardizes a way to do this, essentially. So it puts a transport layer so you can call these functions through an HTTP transport or locally on your machine, whatever. All right. So that's what we do, and we use WebAssembly to encapsulate, to isolate these functions. Okay, this is not a product picture, so I'm done with this. I just wanted to show you a quick demo that's related to this. All right. So let's say that I want my LLM to read the Hacker News front page. Oh, that's not what I wanted to say. Yeah, that's not it. There you go. Let's see if it actually works, because that's a demo, right? What logo?
I was just complaining about the light mode.
What the
Never
fuck?
mind.
Okay. All right. Read the Hacker News. Read the top 3 items on the Hacker News front page. Let's see if it actually works. All right. Obviously, it's not working right now, so let's keep the demo. And if we have time, I will do it later. What's going on here? Yeah, this is running. Why? All right, no demo. Well, luckily I have the transcripts of the demo, so I can show you the demo even though it's not live running. So essentially, the demo is unless you have a way to parallelize the task, if you have a tool, let's say called fetch, that fetches the fetches the URL and gives back the result to the LLM, the way the execution will work will be just like this: fetch, 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 and all of these will take some time, and so it's not efficient, right? If there's a way to parallelize, that would be better. So one of the things that I've been experimenting with in the last few weeks, well, last week actually, couple of weeks, is to create a way to parallelize. That's the reason why I was interested in this paper. And essentially, I can provide this summarized tool that is working using primitive that we have on MCP run. And it's really, it allows me to create processes that are asynchronous, and so that I can spawn multiple of them, like as if they were thread, and then check their results, and then they can run in background in parallel. Anyway, let's get back to the paper, though. Yeah. All right, yeah, the demo was called minions because the processes I call minions, so you can spawn your minions and collect the results. And this is the way, the reason this works for so-called embarrassingly parallel tasks. I don't know if you are familiar with the term. Embarrassingly parallel means things that can be trivially parallelized because you can run them because they're not related to each other. Their results is not related to each other. And I was wondering why it's called like that. It apparently comes from Cleve Moller, I don't know, the creator of MATLAB. They're called embarrassingly parallel because they're so easy to parallelize, it's almost embarrassing to not do so, apparently. All right. Okay, but let's talk about the paper. All right, as already explained, this was, okay, the first paper that talked about function calling was called React. And in React, the LLM calls a function, analyzes the outcome, the reasons, and then reasons about the next section, which is exactly how it works currently. Most LLMs, most services, Mistral, OpenAI, Claude, they all work like that. There's some. I think OpenAI and Claude allow you to flag it for parallel execution. I don't know how that works exactly, but you know, it's 10 months, so. obviously they have implemented it. All right. The problem are all those problems you can imagine, right? It's sequential execution. There's high latency because LLMs are not fast, and you could have also potential accuracy errors. All right. So here's an example that comes from the React paper, and compare with what is actually done with this new paper that we're describing here. These measures are something that are not super happy about them. We can take a few minutes later to discuss them later if we have enough time. But all right. So the first example, were Scott Derrickson and Ed Wood of the same nationality? Who are Scott Derrickson and Ed Wood? Exactly. I didn't know either. They're two directors. All right. So how would React work? Which is, again, how most LLMs would work now. First, it searches for Scott Derrickson, and then it searches for Ed Woods, and then finally gets to the conclusions. And I think I also have an example here because I think I did this one. Yeah, probably. Oh, there's the Nobel laureates, which is another example. We can take a look at that later. Anyway, yeah. So how does this work with the LLM compiler? So we have three components in the LLM compiler. So we have tools, right? Okay, first of all, we're going to talk about function calling planner. All right, we have tools, and the only built-in tools here are the search tool and I think a fetch tool to read the contents of the web page. So the function calling planner will create a directed acyclic graph of tasks, and it will create some sort of plan, some sort of pseudocode of the sequence of operation. It will also use some placeholders to represent the results of every tool call, so they can then refer to it if necessary in other steps. Now, we know that the first search and the second search are independent, so we know that we can do parallel tool invocation. And then we get the results, so we join, and then we have to do a final step that is inherently non-parallel, which is just drawing the conclusions. All right, and there's this measure of latency speed up, which is, yes?
How does the model know that the two searches are orthogonal, independent? Okay, that's
the model knows. All right, I mean, in fact, that's one of the points of the paper is that basically all the components except the tools are actually smaller, potentially smaller LLMs. So how does the function calling planner knows that the two tool calls are independent? Well, it knows because it's an LLM, so it knows that it can do those. Those two requests are not correlated.
The planner itself is essentially an LLM.
The planner itself is
Analyze the prompt and say like,
Exactly.
list all the functions that are independent,
Exactly.
something like that.
Exactly. That's exactly how it works, which is kind of.
Basically, it's the very same model you're describing. The RPC could actually call other LLMs.
That's
basically.
exactly how it works.
Okay.
And that's also how the other thing.
Oh, sorry.
No, it's not really a spoiler on it. That's also exactly how MCP.run works. We have these things called tasks, and essentially the minions are a prompt. And you can't really read this one. Oof. So yeah, you're a minion, helpful, reliable assistant that executes tasks defined within minion tags, and you do SQL injection as a service. Okay. That's what we're reduced to doing now. Strings concatenation. All right. Okay, so these are the three components I was telling you about. There's a function calling planner, formulates execution plans for function calling. It identifies the dependencies between the tasks, right? And then creates a directed acyclic graph of tasks. How does that work? It's a prompt to another LLM. That's how it works. Then there's a task fetching unit that dispatches function calling. I think this is actual code based on dependencies. The one thing that it really does is replacing the variables with actual values. I don't know if the replacement is done through string replacement or it's another prompt. It's possible. I don't know. The code is online though. And then there's the executor. This actually executes the tasks and potentially executes them in parallel if possible. And then obviously manages and schedules the task that has to be called later. Oh, this is a more interesting example. All right. So we have 3 tools, but the third tool in the list, LLM, it's another LLM. So we have search, we have math, and then we have LLM. So the query is, how much does Microsoft's market cap need to increase to exceed Apple's market cap? All right. So we'll do a search for Microsoft market cap, a search for Apple market cap. This can be done in parallel, right? And then obviously the math expression must be evaluated after the other two, and the same for LLM, which is depending on just one result. And as you can see, this task fetching unit is the one that is fetching the task to execute, and then we have the executor where we, send a task for executing, and the diagram explains how they work. For each tool, there's a memory, right? And there's, in a separate space, there's the tools that we have available. So the executor essentially instantiates a tool with its own memory to do the specific call, right? And that's how it works. All right. Yeah, so this is an example, all right. So, okay, one fancy feature of the paper is this dynamic replanning. Essentially, depending on the flow, it might not, the scheduler might not be able, no, sorry, the function calling planner might not be able to describe fully the sequence of the tool calls. It might have, depending on the results, might have to do some further scheduling. So this dynamic replanning essentially allows you to send back some partial results to the executor, from the executor to the function calling planner, so they can emit more tasks to execute. That's particularly useful when it is not really possible to fully explain statically the control flow diagram for the execution. All right. So problems with conditional execution paths when they're not easy to infer. And there's also this game of 24 benchmark that I haven't fully investigated, but it's from another paper, and it's a problem where essentially, I think it's a problem where essentially at every step you discover more of the next steps. So it has to be iterative. All right, okay, and then they do some comparison with the existing approach. So reactive was, as I mentioned, the original approach. I think it's the first paper about function calling. There's also the OpenAI, so the state of the art at the time, there was already OpenAI function calling. So what are the negatives of these problems, of these approaches? Reactive was, first of all, was old. Sequential reasoning, obviously, we already mentioned that. High token usage, apparently, that's how it worked. The OpenAI downsides are a bit more flaky, in my opinion, because the thing is, it's limited to OpenAI proprietary models. Yes, right? But yeah, the point is, if you want to do function calling on an open source model, you don't really know how to do it unless you do React, but React is more complicated. And higher cost, whatever this means, than LLM compiler. There are actual numbers on the paper, actually, but so the good point about the LLM compiler is that it works both with open source and closed source models because it's essentially implemented in a way that can be plugged. So they can plug it on top and then do these fancy function resolutions. Yeah, that's what we said. All right. So in the paper, they provide a few examples. And I think in the next few slides, we also have the examples. Essentially, these are benchmarks that are detailed in the paper with comparison with GPT 3.5. From the names of the models, you see that this is old. So GPT 3.5 Turbo, GPT 4, Llama 2. So this is kind of old. All right. Okay. Yeah, I don't know if I think I forgot one of the pictures. I wanted to show you one picture that is missing here. Yes. So these are the other tasks. So one was the sales forecast. Again, this is parallelizable in this way. This was interesting. because it's more of a tree with more dependency. So if Stanford and UCLA were to merge, will they have more Nobel laureates than UC Berkeley? And you have 3 parallel search tasks, and then you can parallelize the math problem, and then, well, you cannot really parallelize, but you can do one sum here and then another one here, and then you have the output. So the thing is, they did this whole architecture to do the scheduling of tasks. And I realized independently, because I didn't read this paper yet, that at least now, because of the advancement also probably in the models, it's really just enough to use a good prompt, and essentially the LLM itself can do the planning and call the functions in parallel. So in this case, it's just telling it, create a plan and efficiently execute the following prompt, parallelize the execution of the plan whenever possible. If Stanford and UCLA, da 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 da, it creates the plan, which is a common strategy nowadays. You tell it to do a plan and then to follow the plan, and then it will create the minions and wait for the results of the minions, and then it will do whatever is needed to do to give you the answer. Yeah, this is another kind of problem with the same approach. It's just that it's 4 searches and 2 math expressions in parallel, which has the higher total healthcare expenses, Florida or New York, considering both public and private sectors. And we also have this one, same approach, same prompting, which is higher, and it will do the research plan, and it will perform the search. Da, 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 da. In this case, actually, it did the search sequentially. All right, let's get back to slides. Yeah, and there's a bunch of, they did this evaluation. So the embarrassing parallel task was the first one, which was the, Scott Derrickson and Ed Wood. And then there's also the Moby recommendation. The thing that I'm not super satisfied about is that this cost reduction, because I feel like they're not really, they're kind of end wavy. They say this costs less than ChatGPT because ChatGPT will do this sequentially, so it will consume more tokens. Right, but if you're using another LLM to do the planning, aren't you consuming the tokens for that LLM? Now, it is true that they're also using Llama, and you might use another LLM which is more cost effective to do those planning. So yeah, in a way it is fair. It's just that the numbers, I don't know. Yeah, these are just other results. If you're interested in the results, I invite you to take a look at the paper. Obviously, the paper says that they have improved over the state of the art. Otherwise, it wouldn't be published. Another optimization that could be done is that I have a planner do streaming. So instead of just doing the planning, which takes time and obviously increases latency because you have to wait for the planner to do the work, is to have some sort of streaming planner that gives you some results as it goes. That's it. Another thing that it's interesting, obviously, even though it's, again, to me it's a bit of kind of obvious, but I think there was a slide about strangling. Oh yeah, there it is. So this is kind of obvious. As with any parallel load, spawning parallel task is not free, because there's a fixed cost when you spawn a parallel task, and even more so in this case when the architect, it's not threads. It could be threads, but it's threads with an LLM. So they take some time to start working. So all of this work has a cost, and obviously it's not like if I spawn 3 parallel tasks, it will be 3 times as fast. Obviously, there's a curve that you have to go over to. There's a cost benefit kind of balance here to strike, and they do evaluation of that too. All right, yeah, that makes sense. That's it. So if you're interested, the paper is this one, and if you're interested in the code is open source. It's a Python code base, and it's pretty streamlined. It's not a lot of code, so you can take a look and decide for yourself. So that's it. Thank you. And we're out of time, so if you want to ask any questions, we'll do it outside. See you.